Welcome everyone to our fifth weekly discussion session of the Physics of Nanoscale Devices NPTEL course. My name is Jyotishwaran. I'm a PhD student from the Department of Electronics and Communication Engineering, IIT Roorkee. So moving on to the topics that we shall be covering. Continuing from last week's topics, where we arrived at the expression for the stored charge and current in a ballistic channel, we shall now move on to the concept that is known as the modes in a ballistic channel. Now, modes have to do with the conductance properties of a ballistic channel. So, modes are crucial, they are integral for defining the conduction properties of a ballistic channel. So, that is why we shall be looking at this. So controlling the number of modes present in the channel will enable us to change the conductivity and bring it to a desired level. Additionally, we shall, and therefore it is important to learn about the notion of modes. So first we shall look at the concept of modes, like where this quantity comes from, and then we shall go back and revisit the notion of the transit time in a ballistic channel. This transit time was used to derive what is called the energy, what we called the energy broadening last week. So this is related to that. So energy broadening, we denoted it by gamma E. And then we'll see an interpretation of the idea of modes, like what do modes actually mean in a ballistic channel, and then we shall look at the distribution of modes with respect to the electronic energy. And finally, we shall conclude today's discussion with generalizing this ballistic channel, ballistic conduction model to the diffusive limit. Diffusive conduction is what we have in a classical bulk scenario. So we will try to essentially move from the ballistic limit to the diffusive limit, and we'll see what are the defining characteristics in such a situation. Alright, so let us begin our discussion in earnest. So as discussed and derived last week, the current in a ballistic channel is given by 2q upon h gamma e, this is the broadening, times pi into dE by 2 times f1 of e minus f2 of e time integrated over energy. So d of e, this is the density of states. Now I should clarify here, I should have done this last week, but okay, fine. So this is density of states. This is a particular quantity. This is essentially the density of states in the channel. So this is not only the quantity that we have seen derived in weeks prior, but this is more precisely dependent on the geometry of the channel, the dimensions of the channel. So this will essentially be the density of states expression that we derived multiplied by the associated volume of the channel. So we'll see what is the difference between this and the derived quantity, the expression for density of states that we are familiar with as we move along. Now, I'm going to make a statement here which is that this quantity, the second quantity in the integral, which is f1 of e minus f2 of e, that is the difference between the Fermi distribution function from the source side and the drain side, or however you would like to look at it. If you have two electrodes on either side of the channel, these are the Fermi functions of them. What I'm saying is this is the probability of finding a conducting electron at energy level E in the channel. Now, what do I mean by this? We will see. This is going to be our first exercise problem. And whatever is left in our current expression, this quantity, this is what we shall call the modes. So, this is what we are going to call M of E. What I'm saying here is this quantity here, let me use a different color. Yeah. So this quantity over here, I'm saying is the probability density of finding an electron. Because essentially, what is happening? So now, why am I so keen on calling this the probability density? If we go back to our device picture, like the devices that we are studying thus far, it is an electrode, like essentially two electrodes, which are bridged in the middle by a channel. Now, a short channel. Now, the contacts are considered to be bulk elements, and the channel a is significantly smaller in scale compared to the contacts. So these are bulk materials, and this is not a bulk material. This is on a microscopic, or not even a microscopic. This is at the mesoscopic scale. So here the length is of the order of nanometers. I'm sorry. So now what we have to understand is the process of conduction is actually an electron present over here moving through this channel, ballistic transport, and arriving at here. So I have my domain 1 and contact 1 and contact 2. So essentially the electron leaves the bulk material, enters the channel, and then leaves the channel and enters the bulk material again. This is the conduction process. So such an electron is what I'm calling a conduction electron. Okay, so what I'm saying is this quantity somehow represents that probability of finding a conduction electron at a given energy level. And the rest of this is known as the modes in the channel. Okay, so with that, let us move to our first problem. So first question is, show that this quantity is indeed the probability of finding a conducting electron at energy level E in the channel. So how shall we go about this? So let us first consider the case. So we shall do this in two parts. This is essentially going to be a derivation, but we shall do it in a particular structure. So part 1 we shall consider no bias in oh, no bias not in let me say no bias across the device. So when I say no bias across the device, what do I mean? So this is a two terminal device. This implies V, the voltage, is equal to 0. So in this case, what is going to happen? And I'm also going to make another assumption. I'm going to say that, so I'm going to write that here, assuming contacts 1 and 2 are the same material. So the Fermi level, the predefined Fermi level is going to be the same. Like their sizes and their material, it's all the same. Okay, same size and material are of the same size and material. Yes. Okay, so this is an assumption. So in the first case, when V equal to 0, we know no current will flow through. So now that implies this quantity, this quantity which I want to be my probability of finding an electron, this has to be 0. Now we know in this case it actually comes out to be 0 because if I draw the energy diagram axis over here and let us say I am defining my region 1 over here and region 2, like contact 1 and contact 2 over here, then let me divide this into 2, and this is the energy axis. Okay, so now this is not exactly the position axis because I'm going to draw the Fermi function like this over here. So what is going to happen is I will also define the Fermi level somewhere over here. So since there is no bias, this quantity is going to be constant all across, and the Fermi distribution is going to look something like this. We are of course talking about a uh, yeah, oh no, yeah, this curve is hard enough to draw at, oh wow, it's hard enough to draw horizontally. Now drawing it vertically is slightly more, yes, this is better. The entire line is going to vanish because I did it in one shot. Oh, apologies. Yeah, so what I'm going to do is I'm going to draw it up until this point, and then I'm going to start this curve, crosses at the halfway mark, and goes like this. So this is approximately what my Fermi function looks like. Now when there is no bias, essentially the same thing is going to happen here as well. So we are going to have a function that rises through, comes to this point, and roughly, not roughly, exactly equal. So this is going to be 0.5. So this is going to be 0.5. So now I know that f1 minus f2 of e is 0 in this case when there is no bias, and I'm assuming that the materials are the same. Now, if what happens if the materials are not the same? We know that when the materials are not the same, the Fermi levels will still match. Like this has been proven. So the reason I assume that these are of the same size and material is actually to prove the second case, but you can rest assured that even if they are of different materials, different sizes, this thing will still hold because at equilibrium, this system needs to have like the same Fermi level. The Fermi level has to be same across the entire device. So that is a requirement. Okay, so that is like a proper requirement of this kind of a system. Yeah. Yes, somewhat better. So in this case, since they are both identical, this implies f1 of e minus f2 of e is 0. Now, what happens, which implies no current? No current flows through the channel, and this is something that we know. This is something that we have established. So we shall start from this point, like essentially we have started with this point. Now moving to the next case. Now we shall consider case 2, where I'm saying V not equal to 0. So now there is a bias, and let me say that it is, yeah, let me just draw the channel device over here. So this is the setup that we have. So what we are doing is plus minus, and we have a voltage V between this, and we have our channel here. So now what happens here? So we know what happens. We know that because of this, the Fermi level on the contact number 2, on the side of contact 2, is going to be lowered because it is at the negative electrode of the potential source. So it is going to be lowered And this, like, since it's relative, we can assume that EF on 1 is going to stay and EF on 2 is going to come down. So this would imply EF2 is equal to EF1 minus QV. Again, this expression is true even in the case when the materials are not equal. The material not equal, not the same. Even if the geometries and everything changes, this expression still holds. But now we also, and oh yeah, yes, this expression holds because at equilibrium EF2 will be equal to EF1. Okay, so now after this, what happens is, what we can see is, like, graphically we can see this. Yeah, so again we have our region 1, our region 2, and now I'm going to draw two sets of lines. So I'm going to draw a first line that is here, which shall denote EF, or rather let me call this EF1, and a second line, yeah, why not, let's use green, which is going to be below this. Now this is schematic, this is not again to scale or anything. So I'm going to say this is EF2. So now, again the separation line between the two. Now what happens to the probability of having electrons in the respective regions? So what happens is, this is going to be with respect to the first Fermi level. Yeah, I'm going to slide this slightly to the side and say it's going to look more like this. Because of that, I can just use this. Whereas in the second case, what's going to happen is the Fermi function is going to look, it is going to be with respect to this new lowered Fermi level, because the system is no longer in equilibrium. So in that case, you're going to have a Fermi distribution that is going to look like this, which therefore implies that because of this energy difference, now conduction will happen, like, empty states start, like, if this were to be t equal to 0, then all energy levels up to this point will be filled on the contact 2, all energy levels will be filled up to the purple line in contact 1, which implies conduction will occur between these two regions. Now similarly in this case also we can say that conduction is going to occur in these two regions, because for energies much less than EF2, again both of these will be more or less 1. So over there F1 minus F2 will be 0. But where is F1 minus F2 going to be non-zero? F1 minus F2 is going to be non-zero in this region. And remember what was originally mentioned for conduction? I need an electron at a particular energy level here to enter the channel, exit the channel, and occupy an energy level here, which implies I will need an electron to be present in this energy level, and I will need a vacancy at some energy level in the channel. So I need both of those quantities to be present. Now that is when conduction will happen. So then and only then will an electron start from here, enter the channel and leave. So the probability of conduction occurring. So probability of conduction occurring is equal to probability of electron, or rather I shouldn't say electron, probability that energy state, energy state E is occupied in one, in like contact one, multiplied by probability some other energy state. So, oh no, not some other energy state. Now we are assuming that electron with some energy enters the channel and goes and occupies the same energy. I'm sorry. So, energy state, yes. Because if that was occupied here, then by Pauli exclusion principle, the electron cannot enter the channel at that energy. It will need to gain more energy. Okay. So, energy level E is empty in contact 2. So this is the probability of conduction electron. Finding a not occurring probability of conduction electron existing in the channel. Okay, so it is the product of these two probabilities. Now, from our previous discussions, we know that the first probability, therefore probability, yeah, now I'm going to use the short notation, finding conduction electron in channel. We know the first quantity is F1 of E, because that is the probability of finding an electron at energy level E, multiplied by the quantity 1 minus F2 of E. Okay, so now the product of these two is going to be F1 of E minus F1 of E into F2 of E. Now, this is not what we saw in our previous expression. However, here I'd like to point out that because of the bias that we have applied, because of this case, at any energy level, like provided a bias like this is applied, we are assuming conduction from 1 to 2. An electron is leaving this channel and leaving this contact and reaching the second contact. We can say that this quantity is always going to be greater than this quantity here. In fact, for a significant portion of this region, f of e is almost 1 over here. So this is 1 for the Fermi distribution function, if you remember from our previous discussions. So the point at which this starts having values less than 1 is much sooner, like this is the energy axis, is much earlier, like for much lower values of energy, empty states will start appearing here. So if I'm talking about an electron with energy E moving to a state here, then I can assume, like in this product, since this is almost 1, what I can do is I can assume this to be approximately equal to 1, which implies this quantity is approximately equal to F1 of E minus F2 of E. So this is the probability of finding a conducting electron in the channel. Now this is, again, I'm talking about it in this sense. So this is the probability of finding a conduction electron in the channel, and as we discussed, as I mentioned before, over here, these are the remainder are the modes that are present. So now the derivation for the expression for the modes in the channel must have been done in the lectures. I don't want to walk through the entire derivation again. So we shall start with the results themselves. So For a 2D channel, the mode distribution with respect to energy is given with respect to the average velocity in the positive x direction, which I call Vx plus of E, as this. So this quantity here is m star, like effective mass. Okay, so m star by pi h squared. So why are we using the effective mass over here? Because going forward, we shall look at density of states in the conduction band. Now, why are we looking at density of states in the conduction band? Because we are looking for conducting electrons. So conduction electrons, like coming from the contacts. Now the electrons will be conducting electrons if and only if they are present in a partially filled or an empty, like a previously empty band, like a band that is empty at t equal to 0, or a band that is partially filled at t equal to 0. Then and only then will conduction, like that electron, be capable of conducting current. Just 1 second. Yeah, I'm back. So just, yeah, one more clarification. So what I'm going to say here is this bias is non-zero and it is also large. Okay, so for a large bias, this is true. So if this is very big, then we can see that clearly this will be 1 for a very large fraction. So because of that, this approximation will hold. Okay. So this result is true for large bias values. True for large bias values. Now what happens when the bias values are small? That will be covered in the next week. So that will be the central topic for week 6. So I will not spoil anything right now. When week 6 begins, we will see what is there in it. Okay, so now this quantity d2d of E is this. This is the density of state function that we derived. Similarly, we will have functional forms for d1d of E and d3d of E. Now d of E that we wrote will essentially be, in this case, d2d of E multiplied by the area of the channel, because this is a 2D channel. So the volume, essentially the extent of the spatial extent of this channel, is denoted by its area. For a 1D channel, the spatial extent will be its length. For a 3D channel, it will be the volume, the length into width into the height or depth of the channel, whatever we'd like to call it. And this quantity for a 2D channel specifically has a connection to the de Broglie wavelength of the electron. So the quantity de Broglie wavelength we shall represent as lambda b. So this again is a function of the energy. In fact, it's a function of the momentum. But since energy itself depends on momentum, we can say that in a fashion this depends on the energy of the electron. And m of e, of course, since it's a product of two functions of energy, it will have an energy dependence. Now, just like density of states itself, we know density of states d1d of e is proportional to e to the power minus 0.5. d2d of e, as shown here, is a constant, so that's proportional to e to the power 0, and d3d of e is proportional to e to the power 0.5, like square root of e. Now, the mode distribution is dependent on energy as e to the power 0.5 plus d, where d is this quantity. It is either minus 0.5, 0, or plus 0.5 for 1d 2D and 3D channels respectively. So the mode distribution M of E, and with respect to E, if we are considering a 1D channel, then it is proportional to minus 0.5 plus 0.5, that is E to the power 0. So it will be a constant. And a 2D channel, it will be proportional to E to the power 0.5. For a 3D channel, it is going to be proportional to E. So as and when the energy increases, the number of modes in a 3D channel increases linearly. Now we shall look at, so we have seen the like essentially how we are defining modes. We have seen through problem one, like one part of the integral we have shown that it's the probability of finding the electrons. Whatever is left, we have just chosen to call it the modes. We have defined modes, we have seen the expression for the modes, and we are seeing the energy dependence of the modes. Now from that, let us first look at N2D of E and the connection between the de Broglie wavelength lambda p. So we know that M2D of E is equal to H by 4 Vx plus of E into D2D of E. Now we know D2D of E is, so now let me just write the expressions here. So now this quantity here, this is 2 pi, sorry, not 2 pi. This quantity is 2 by pi into Vx. So we know this, like essentially how do we arrive at this? We consider a 2D channel like this is the y-axis and this is the x-axis, and then we look at electrons that are essentially like they are moving in all possible directions. So I have the angle theta, and theta can vary from like 0 to pi, or we can say like if we are keeping theta equal to 0 along the x-axis, then it can vary from minus pi by 2 to pi by 2. So after that, we essentially the direction velocity along the positive x direction will be given by the total velocity v cos theta. So the average positive velocity v plus x of e will be given by, sorry, angular bracket here. This will be equal to integral minus pi by 2 to pi by 2 v of e cos theta. We are assuming that there is no angular dependence times pi. Now, sorry. Yeah, this integral can be evaluated and we will find that this will come out to be minus sine theta. From that we will get a factor of 2. So the average velocity is not Vx. Sorry, I shouldn't have said Vx. It is V of E. Yes. Okay, so this quantity is V of E. So I'm just going to write it as h by 4 2 by pi into V of E into m star by pi h bar squared. Now m into V of E can be seen because now in the ballistic limit we are actually considering our electrons to be semi-classical particles. Like this is a semi-classical treatment. So ballistic conduction, this model itself is semi-classical. Like it's not a fully quantum mechanical treatment of the process, it is a semi-classical treatment. So in this semi-classical mode, we can assign quantities, we can call momentum as mass into velocity. So n star into V of E becomes the momentum. So this quantity is now h by 4 into 2 2 by pi u of e into uh, yes, sorry, let me bring the m star over here by pi h bar squared. Yes, so now this will become p. Yeah, the second multiplication sign is not needed here. So now this will be h by 4 into, what I'm going to do is I'm going to take the 4 over here. So I'm going to write this whole quantity as, or rather I'm going to bring the pi squared over here. I'm going to send a factor of 2 here and bring over a factor of pi here. So what we are going to have is h by 2 pi into 2 by 2 into p by pi h bar squared. Now h by 2 pi is h bar, so one h bar will cancel out the other in the denominator. So what we are left with is p by pi into h bar. Now lambda b is equal to h by p. Now this is again h by 2 pi, the pi will cancel, so this will become 2p by h. Now h by p is lambda, so this whole quantity will become 2 divided by lambda b. Or rather, let me not send this answer to the corner of the screen. Let me just do one thing. Let me just select this whole stuff and move it slightly above. Yes, everything over here. And let me move it just, yeah. Oh, somehow these didn't get selected. Yes. Yeah, now we have enough room. So now this quantity, I can write this as, after all the cancellations, this will be 2p by h. Now this is the definition. So therefore m2d of E is equal to 2 divided by lambda b of E. So this is how it is related to the Debye wavelength at a given energy. So this is the relationship. In the lecture, what you will have seen is, now this is the mode density. The total number of modes is given by, now M of E for a 2D channel. Let me do that in a new slide. Yes. So now we know M of E is equal to the width into M2D of E. Okay. So because of that, we can now say M of E is equal to the width of the channel divided by lambda b by 2. So this is what is mentioned as the number of half wavelengths. So the instructor, Professor Vishwen, would have mentioned this half wavelengths in the channel. Like It's not even in the channel. Number of half lengths, half lengths. I'm sorry, half wavelengths along the width of the channel. Okay. So essentially, if we have a 2D channel that I'm representing like this, then we consider the number of half wavelengths. Like, I mean, if I'm looking at the full wave, I'm supposed to go below, but just for the sake of representation, like this essentially corresponds to this. Okay, so just remember that. So if I can accommodate 3, then the number of modes in this 2D channel is 3. Therefore, M of E is equal to 3 in this case. If we have a shorter channel, then it may be 2. If there is even shorter, then we will have 1. And this quantity we will always round up to the nearest integer. Like number of modes, it's a number. It's a discrete quantity. It's a whole number. Okay. So now you can actually, the length of each of this thing is lambda b of E by 2. Okay. Now this will actually tell us, if I'm given a channel of, like, okay, let me pose a fresh question right here. In such a 2D channel, in a 2D channel, what is the maximum energy and not an a conducting electron can have? So this is my question. In a 2D channel, what is the maximum energy a conducting electron can have? Now, for an electron to be a conducting electron, we need two quantities. Again, let us go back to our original expression. We need two quantities. We need an electron to be present, that is the probability factor, and we need a path through which the electron can traverse the channel. Those are the modes. Now, we have said that in a 2D channel, the number of modes is the number of half wavelengths that can be accommodated. Additionally, I am going to say this is also true. E is equal to P squared upon 2m star. So this classical expression of energy is what we need to take. Okay. So now that we know this, now we can definitely say, okay, so now this is the question. Now how do we go about answering this? Let me not directly explain the answer. Let me go about this step by step. Okay, so here we are. So first we know that E is equal to P squared by 2m star. Since this is true, this implies P of E, now I can write this like this, is going to be square root of 2m m star E. So this is true, which implies lambda b of E is equal to h by square root of 2 m star E. Now, like to be more precise, what I'm going to write here is this. M of E is this quantity. It is W divided by lambda b of E by 2. So this denotes, when I put brackets like this denotes what is called the floor of a number. So this is, it's called the floor. Like in computer science terminology, it's called the floor. For more formal mathematical notation, this is the greatest integer function. This is the greatest integer function. So greatest integer function says, given a number, it will give out the greatest integer that is less than or equal to the given number. So this is the greatest integer function. For example, 2.5 will be 2. Even if it is 2.9, it will be 2. Because it is the greatest integer less than or equal to. Now 3 is an integer, but it is greater than 2.9. So that is the thing about floor. Floor will just drop the decimal point and take the number. There is another function called ceiling which will take the number to the right, and then there is a nearest integer function which will depend on which side of 0.5 it is. So this is more accurately the number of modes. So if I had a channel where instead of this, let us say we had, like, let me just draw that here, let us say we had 1/2 wavelength and just a quarter of another wavelength, then this won't be considered. There is only one in this case. So in this particular case, I can say m of e is equal to 1. It is not a 1 point something. It is just 1. Okay. So coming back to the question. So we know this is lambda b. And from this we also know what lambda b by 2 is. Now, what is the greatest energy? That is what is asked. So essentially what we need is W by lambda b of E. Let me just take that 2 to the numerator. So 2W by, now for conduction, number of modes should at least be 1. Okay, so there should be at least one mode present, which implies W divided by, yeah, let me use the standard thing itself, lambda E by 2 should be greater than or equal to 1. Okay, this implies this further implies W divided by, now let me take the 2 to the numerator and write this as h by square root of 2m star e should be greater than or equal to 1. Which implies, now this will go to the yeah, this should be greater than or equal to 1. Yes, yes. So this implies, yeah, square root of 2m star e into 2w divided by h is greater than or equal to 1. So starting from that, it will further imply that square root of 2m, just 1 second, let me just be sure I'm not making any mistake here. Oh, sorry, did I say maximum energy? Yeah, that was my problem. It is the minimum energy. Yeah, that's where I made a mistake. Apologies. So it is a minimum energy, not maximum energy. Yes. So this will be greater than or equal to h divided by 2w. Like essentially whatever I had here, I took the w and h factor over here, and greater than or equal to square, which implies 2n star, yeah, again star over here, not to forget, The reason we are using M star is now we are formally saying that we are in solids. Like, the rest mass of an electron is no longer relevant. Because depending on whether we are in the conduction band or valence band, this quantity can also be negative, as we have seen before. So this is greater than h squared by 4w squared, and so greater than or equal to. So finally you can take everything over there. This implies the minimum energy E min is equal to h squared by 4 m star, or rather 8 m star, m star w squared. So this is the minimum energy an electron needs to have to be conducted through a 2D channel, because less than this there are no modes. So even if an electron exists in contact 1 and even if that state is empty in contact 2, there is no way it can travel through a 2D channel. Okay, so this is important. Conduction and the concept of modes therefore tells us at what energy electrons will be conducted through a given channel. Now, as we have seen before, for a 1D channel, the number of modes is independent of the energy, which implies electrons of all energy will be conducted through that channel. Now here, we have seen that a minimum energy is required. And we shall again see, not of all energy, okay, I shouldn't say of all energy. What I should say more precisely is the number of modes does not vary with energy. At any given energy, the number of modes is going to be constant. Like below a certain energy, even for a 1D channel, it may become, no, will it become zero? No, actually it won't. I was correct initially, yes. Electrons of all energy will undergo a 1D channel conduction, but here there is a cutoff energy, and that cutoff energy is this quantity. Now, usually this quantity will be like too small, like E min will be too small. It will be very, very small compared to the average electron energy, but nonetheless, this quantity is present here. Like this may become relevant when we are talking about, say, extremely low energy systems or things like that. But from a theoretical standpoint, this is important. So 2D conduction will occur if and only if the electron has an energy that is greater than this. Now, why did I solve this? So this is the, let me just write it here. This is the minimum energy required for an electron to undergo 2D ballistic transport. Like, I mean, we can actually do a rough calculation. So, if we take, say, channel width to be approximately something like 5 nanometers, then in that case, this will, let me quickly, like, since I came up with this question right now, I have to do these calculations myself. And let me assume m star is equal to the mass of the electron. For now, just for the sake of example, because usually the effective mass is like lesser than the mass of the electron. So, I'm just assuming a slightly, idealized case where it is equal to the mass of the electron. So, in this case, let us see what the value comes out to be. So let me just calculate this. So I have that 8 into, so we have the mass of electron, which is further multiplied by 5 nanometers squared, right? So 5 10 to the power minus 9 whole squared. So this will come out to be something like, yeah. So for these two values, E min is approximately equal to 0.015 EV. So as you can see, and as W increases, as the width of the channel keeps becoming bigger and bigger and bigger, this quantity will become smaller and smaller and smaller. So as you can see, this quantity is very small. Like this is 15 milli electron volts, which is a very low energy in terms of like conduction properties. Like typically conducting electrons have to the order of a few electron volts. Like if you are looking at atomic energy levels, then the ionization energy of the hydrogen atom is around 13.6 electron volts. So compared to that, this is like 1/1000th of that approximately. So this is a very small energy value. So albeit this is there, but this usually doesn't have much of a bearing on the realistic scenario. Okay, so moving on. Now we need to derive the expression for the positive x direction velocity for a 1D and a 3D channel, assuming that the velocity is independent of the angle. So first we shall look at the simpler case, the 1D channel. So in the 1D channel, oh sorry, that's a very very bad straight line. Yeah. So yes. So this is my channel. Like if I assume this to be x equal to 0, then I can have velocity v going either in this direction or we can have velocity v going in this direction. So, so we can have an electron that has velocity v in this direction. We can have velocity v in this direction. So this is minus v and this is plus v. Now the probability of this occurring in a 2D channel is, in a 1D channel is equal. So like we are assuming, there is no particular bias in the motion, which implies, and the velocity cannot have any other components. Like there is no cos theta to be taken here. It's either plus v or minus v, which implies vx plus of e is simply equal to v of e by 2. That's that. Okay, so 1D channel, the answer is pretty straightforward. So this is half of the velocity of the electron. But what happens in the case of the 3D channel? So yes, now for the 3D channel. For the 3D channel, we need to, like, oh, why did I put 3? Yeah, I was saying 3D and I decided to mark the number 3. So case 2, which is the 3D channel. So now we have to consider all possible directions of motion. So let me represent my 3D channel like this. So this is the x direction, this is the x direction. So Okay, so now let me pick a point over here. Now the thing is, let me view it from this direction. Okay, this is my direction of viewing. So in that case, what is it going to be? And this, if this is the x-axis, then let me assume that this is the z-axis. Therefore, the y-axis is what I'm looking at. So this is the z-axis. This is the x-axis. I'm drawing it dotted because I'm showing that this is in a certain perspective. So this point that I'm seeing here will be like this, and electrons can move along all of these angles. So all these angles are possible. So I will consider one such position and mark the angle theta. So here it will be actually easy for us to use the polar coordinates. That is why I am viewing it along this. So the angle made with the z-axis is theta, and the azimuthal angle, the rotation about the xy plane, the rotation about this plane, this rotation is represented by an angle phi. So over here, therefore, what is the velocity of the electron along the x-axis? In polar coordinates, we know Vx is equal to V sine theta cos phi. We know this to be the thing, like this comes from the polar coordinates. Okay, spherical polar coordinates to be more precise. Because polar coordinates, we also have 2D polar. So, spherical polar. Coordinates. Okay, so we have spherical polar coordinates, and v of x is given by v sine theta. Like it's essentially it is the component along the xy plane projected onto the x-axis. And what is, for it to move in the positive direction, what are the allowed values of phi? Phi starts from 0 at the x-axis, so it can go from minus pi by 2 to pi by 2. And similarly, and theta can vary from 0 to pi. So theta belongs to 0 to pi, and phi belongs to minus pi by 2 to pi by 2. So we need to do two integrals. So we can either do them in sequence or we can do them one after the other. And we know the length of both of these okay, so before we start integrating, yes, so this is there. Now what we need to remember is, okay, so let me not say that yet. So now Vx plus of E. Now here, assume that all of this is at a particular energy because there are too many symbols already. So I'm just going to write this like this. It's going to be integral, yes, 0 to pi and 0 to, not 0 to, this is going to be minus pi by 2 to pi by 2. This is going to be a double integral v sine theta cos phi. Now this is the thing here. What is the integral factor here? What is the volume element? So the volume element in polar coordinates is not just d theta d phi, it is actually cos theta d theta d phi. So like essentially a volume element like dv in 2D space, dv is given by uh, dx dy, but in spherical polar coordinates dv is given by r squared cos theta dr d theta d phi. So this is the volume element. Now, of course, we are like the length of the thing doesn't matter. We are essentially just V does not belong as depend on the angles, so that quantity won't be here. Therefore, we can say that we are integrating over the unit sphere essentially, and uh, this quantity here is like this will become 1. So we have cos theta, and since there is no r dependence, dr will also vanish, d theta, d phi. So this is the integral that we have to perform. So first we have to do sin theta into cos theta, that will be sin 2 theta by 2. So divided by, like there will be 1 pi for this integral and another pi for this integral. So it's going to be divided by pi squared. Okay, so the first integral is going to be sine 2 theta from 0 to pi. Now sine 2 theta varying from 0 to pi is the same as, wait, am I saying that correctly? Yes, so, oh yes. Huh. So integral minus pi by 2 to pi by 2. So what I'm going to do is I'm going to just, in fact, it would be easier to do the cos phi integral first because the theta integral has some dependencies here. So cos phi is just going to become minus sine phi from this. So that is going to give me a factor of 2. So I will just write the factor of 2 here. Integral 0 to pi v sine theta. Is it r square cos theta or is it r square sine theta? Oh my god, yes, I made a mistake. The volume element is not r square cos theta, it is r square sine theta. God, I'm really sorry for that mistake. That was a very silly mistake. Yeah, it's r square sine theta dr d theta d phi. I'm really sorry, I was not thinking straight. Yes, now we are good. So the d phi integral, because otherwise the thing will vanish and I was just having a small crisis here. So d phi is just cos pi from minus pi by 2 to pi by 2, so that comes out to be 2. And yes, now we have another sine theta here, d theta, yes, divided by pi squared. Now this is going to be sine squared theta, so that is that will be 1 minus cos 2 theta by 2. Yes, so it's going to be 2 integral 0 to pi 1 minus cos 2 theta whole divided by 2 into v d theta. Now we know cos 2 theta will complete a full period, therefore the volume under that curve is going to be 0, and this, the only factor is 0 to pi over here, so that will give us a factor of pi by 2. So since we are integrating from 0 to pi, so we will get divided by pi squared, sorry. So continuing to the next slide, this implies Vx plus, for the 3D case, let me just write that here, is equal to integral 2 into integral 0 to pi v 1 minus cos 2 theta by 2 d theta divided by pi squared. So now this quantity is going to be 2 into pi by 2 into v divided by pi squared. So this 2 and 2 will get cancelled and this pi will get rid of this factor of 2. This is equal to v by pi. So in the 2D case, average velocity was 2v by pi, and in the 3D case, it is going to be, therefore now I can write the complete expression. Vx plus of E 3D is equal to V of E divided by pi. So this is the average positive direction velocity in a 3D channel. So this is the quantity that needs to be plugged in when we are considering the 3D channels. Of course, mostly we shall be looking at 2D channels because They are the ones where like the calculations are simple and they are also more relevant because now the need of the hour is the construction of more and more planar or less than planar devices. We need our devices to be not only small in scale but also like more compressible so that we can stack more of them on a given die. So silicon die. So 2D devices are going to be the most relevant examples that we are studying, but nonetheless, for the sake of completion, this derivation is done. And before I move further, this whole problem, this particular problem, I did not do for some random reason. I didn't do it because I just wish to do it. This is important for answering one of the assignment questions. So if you go through your assignments, you'll be knowing which is it, and hopefully what is done here should help you solve the assignment question. So finally, we come to the generalization to the diffusive limit. Now this was the last two lectures of week 5. Uh, there's a good amount of derivations and things going on in it. However, I'm again not going to walk through the entire derivation. What I will just do is I'll summarize the complete effect. So, ballistic transport. So, what is the ballistic limit? So, the ballistic limit. So, the ballistic limit. So, when can I say that the electron will undergo ballistic transport? That is given by the ballistic limit, which is channel length. I should put equal to colon. Yes. Yeah. So the channel length, I've already mentioned that in the slides, but nonetheless I'm writing it. L should be less. In fact, it should be very less corresponding to the lambda E. Note that there is no subscript here. This is not the de Broglie wavelength. This is the mean free path. Okay. Use a different color just for clarification. Yes. So this quantity here is the mean free path. Okay. So not to be confused with the de Broglie wavelength. I'm using lambda here because that is what has been used in the lecture notes. Ideally speaking, I would have used another Greek letter, but I don't want to induce any more confusion. So this is the mean free path of the electron. Okay. So ideally speaking, we want the channel length to be much smaller. Now, how much smaller, we don't know, but we want it to be very small compared to this. Or to be a bit more generous, I will say it should be small. I shouldn't say much smaller. Oh no, should change color. Yeah. So very small compared to this. Okay. Sorry again. So this is the ballistic limit. So what is the diffusive limit? The diffusive limit is the opposite of this. So the diffusive limit is L is much greater when compared to lambda of E. So what happens to ballistic transport in the diffusive limit? So understand this well. The expression that we are given, so essentially what we are told is in the class, we are told that in the diffusive limit, I is equal to integral, or rather I should say 2q by h integral t of e, m of e, f1 minus f2 dE. This is the expression you will see in the lecture slides in the diffusive limit, where T of E is defined as the transmission coefficient. So we call this the transmission coefficient. Now, and the formula for that is here. So if L becomes very large, then T of E will become 0. Let tend to 0. Does that mean for a large channel no current will flow? But that is not true. Even if I apply a very small voltage and the material is conducting, at least a very tiny amount of current will flow. Like that is bound to happen. So what is the implication of T of E here? Just 1 second. I'm sorry, there was a brief power outage. I hope. Okay, yeah, I'm still connected and the recording is still progressing. Apologies for the interruption. Yes. Uh, so this quantity T of E will become very small. Does that mean no current is going to flow? The answer is not correct. That is not the right statement. The thing that will happen is as T of E becomes smaller and smaller and smaller, the ballistic transport will become smaller and smaller and smaller. That is what we need to understand. Like T of E becoming smaller doesn't mean that no current will flow. T of E becoming smaller implies that ballistic transport will no longer occur in the channel. Now, as T of E becomes smaller, ballistic transport will become the more dominant mode of transport in the channel. Okay, just 1 minute. Yeah, I'm back. Apologies for the interruption. So, yes. So, like, essentially, what we should understand is that there are two competing modes for the electron to move from contact 1 to contact 2. It can move either through diffusion or it can move ballistically. Now, the thing is, diffusive transport, the characteristic resistances are much higher. Ballistic transport, as we will see in the next week, the amount of like the typical values of resistances in the channel, and we will also compare it with the resistances in the case of like bulk cases where the diffusive transport occurs. Um, the idea is as the channel length becomes larger and larger and larger, ballistic transport will occur lesser and lesser and lesser, but diffusive transport will always take place. But as the channel becomes smaller and smaller and smaller, there will be no need for the diffusive transport because there wouldn't be so many collisions occurring. The spatial extent is so small that the concept of diffusion loses meaning. So this is what we need to understand. That is why I'm using the word diffusive. Oh, sorry. I'm using the phrase diffusive limit over here. This is very important to understand. Increasing the length doesn't mean the channel will stop conducting. No, the channel, depending on the charge carrier concentration and all those things, will still conduct. It will have a characteristic conductance or a resistance value associated with it. But the transport, the mode of transport, how the electrons are moving from contact 1 to contact 2 will change. That is all that is changing here. So that is the takeaway message here. However, the expression given here is lambda of E, like T of E is lambda of E divided by lambda of E plus L, where L is the channel length. So based on this, we shall do one numerical to tell what I mean, and then with that we will end today's session. So what we have been told is T of E at some energy is equal to 0.8. Okay, now so this is equal to lambda of E. I'm not given the mean free path. I'm not even giving the channel length. I'm given nothing. Plus L. So this is given. Now what happens if L goes to 10 times L? So what is going to happen to the transmission coefficient? So in order to do that, first I will have to find out what the relation, like I need to find L as a function of lambda E using this quantity here. So that I can do by this. So essentially 0.8 is 8 by 10. So this implies 10 by 8 is equal to 1 plus L by lambda E. Yes. L by lambda E, which implies L by lambda of E is equal to 1 minus this, so that is going to be, is it going to be negative? No, can't be negative. What am I saying? Yes, it will be this minus 1. Yes, so 2 by 8. Yeah, which is 1 by 4, which implies L is equal to lambda of E by 4. So as you can see, even if the channel length is only 1/4 of the mean free path, the transmission coefficient is 0.8, which implies whatever number of modes I have in my channel, only 80% of them will be available for conduction. Okay, so that is essentially what is happening here. Like T of E, M of E, this transmission coefficient diminishes M of E by a factor. So if T of E is 0.8, this implies only 80% of the modes are available for ballistic transport. For ballistic transport. Okay. All right. So now we know the relation. Now what we are told is L goes to 10 times the initial value. This implies the new L dash is equal to 10 lambda E by 4, which implies the new transmission coefficient T dash of E will be equal to, since all of these are lambda E's, I'll just plug in the value and cancel out lambda E. So that will be 1 divided by 1 plus 10 by 4. I hope this is clear to everyone. Lambda E is 1 times lambda E, lambda E is 1 times lambda E, and this is 10 by 4 lambda E. So I've just cancelled lambda E from the numerator and denominator. So this is 1 plus 1 by 10 by 4. So this will be another 4 by 4, 14 by 4, and therefore this answer is 4 by 14, which comes out to be, I mean, it's roughly 1/3. So, but the exact value is, it's essentially 2/7. Yes, it will be 0.29 approximately. Like it's 0.286, but 0.29 is fair enough. Okay, up to 2 decimal places. That implies if I just increase my channel length by 10 times, see, originally 80% of the modes were available. Now less than 30% are available, which implies the number of modes as I increase by a factor of 10 is going to go down by like more than 2 times. Now let me continue this exercise. Let me continue this exercise and say what happens in the case where L goes to 100 times L dash. So in that case, what will we have? T of E is equal to 1 by 1 plus 100 by 4. Yes, 100 by 4. So now this will be 4 by 104. What is 4 by 104? Now you can see that this is only around 4%. So this comes out to be 3.8%. So 0.038. Okay, so this comes out to be, so this is equivalent to 3.8%. So less than 1/10. Like if I increase by 100 times, so let us say initially there were initially there were, oh no, let me write it here. If initially there were 10 modes in the channel, then at n equal to lambda e by 4, number of modes will become, like the effective number of modes will become T of E into M of E will become 80% of this, which will be 8. Now, yeah, and if I go to L dash equal to 10 lambda E by 4, then T of E into M of E will be 29%. Remember, this is less than 30%. So, and remember our discussion from before, it is the floor function, it is not the ceiling function. So, in this case, the effective number of modes is actually going to be only 2. So, originally, although there were 10 modes available, now only 2 are available by just increasing it by a factor of 10. Now, increasing it by a factor of 100, now 4% is 0.4, of 10 is 0.4. So, there are no modes. So, ballistic transport will stop. So this is usually what happens, and we are talking about lengths in nanometers. So even from tens of nanometers, if you go to hundreds of nanometers, which is still sub-micrometer, we will see that ballistic transport ceases to happen. So, but that doesn't mean no current will flow, because we have macroscopic materials through which large currents can flow very easily. So that happens all the time. But ballistic transport will no longer happen. So if I have L double dash, which I say is 100 lambda of E by 4, is actually 25 times lambda E. In that case, T of E, M of E, I'll say it's 2.9, which is not approximately, which corresponds to 2 modes. And T of E, M of E in this case will be 0.38, which corresponds to 0 modes. Okay, so this is what I meant. So 0 modes does not imply that the thing becomes an insulator. It just becomes a poorer conductor. Ballistic transport no longer occurs. Now, how much of a poorer conductor? For that we need to know the values of the associated resistances and conductances, and we need to do those comparisons. That we shall be able to do after the syllabus of the next week's part. I mean, the next week's part of the syllabus is completed. So with that, I will bring this session to an end. Thank you all for listening. We shall meet again, same time next week.